All right, so far we have been dealing with problems in the last section where we're given a table that it represents a linear function. So when you plot the points, they're in a straight line. Life's great, we can find the equation of that line. But in real life, when we're given sets of data, it's not always going to be perfectly linear, okay? So sometimes we're given data points and they're not exactly in the straight line, but they're kind of in the line. We can see that they're increasing, but it's definitely not a straight line. Even if our points aren't exactly in a straight line, we can come up with something called a model or a best fit line or a linear regression model that approximates what's happening with our data. So the idea is these points are not in a straight line, but they're kind of behaving like a line would. They're increasing or they're decreasing. Maybe we can come up with some linear function that closely fits to these data points. It's not going to go through every data point. Probably won't go through most of them. But the idea is the point should be kind of close to the line, and the line gives us an approximation or a model to predict what's going on or find a pattern that's going on with our data points. That's what we're going to be looking at today, okay? So I'll probably summarize in this first thing too. And most data in the real world is not exactly linear. And all we can do is write models that are close to the given values. By plotting the data points, we create something called a scatter plot. So we'll take the data that is given to us, plot those points, and that gives us a scatter plot. And then to determine a linear model that, a linear equation that models the given data, we can do a variety of things. We can choose the first and last point and make a line that goes between those, or we can just ignore the first point and join all of the remaining points. We can calculate by hand or use a calculator to give us the best fit equation. To find this equation, we are going to use a process called linear regression. It's also called finding the best fit line or finding a linear model. All of those terms mean the same thing for us. Unless your data is exactly linear, the regression equation will not match up all of your data points exactly. It is a model to predict the outcome. So as I said, we're trying to find an approximation to the data. Our answer should be, or our line that we find is going to be close to the points, but it might not necessarily go through all of the points, okay, every time. Sometimes it will, most times it won't. Okay, and we're going to do this. It says you can do it by hand or with the calculator. We're going to do it with the calculator because our numbers are always going to be messy. All right, so the first example is a guided example. We'll start off with a table where our inputs are given to us in 0, 2, 4, 6, 8, 10, 12, and our outputs are these decimals. Part A says, based on the table, determine f of 6 and write a specific ordered pair associated with the results. According to the table, when the input is 6, why is it not letting me write? There we go. When the input is 6, the output is 26.24. So f of 6 equals 26.24, and that gives us the ordered pair, 6, 26.24. Okay? It says use your graphing calculator and Zoom 9 to generate a scatter plot of the data. So we're going to take all of the points that are given here, 0, 23.76, 2, 24.78, and so on. And we're going to plot these points. We're going to use our graphing calculator to do this. And the way that we put this into our graphing calculator is to put in all of the inputs in one column, put in all of the outputs, f of n, in another column. And then we'll tell the calculator, hey, my x's are in this column, my y's are in this column, and it'll create the scatter plot for us. So let's do that together. And then after we create the scatter plot, it says, because we're going to do a couple things. For part B, we need the calculator. And then for part C, it says use your graphing calculator to determine the equation of the regression line for the given data. So we're going to plot the points, see if they kind of look linear, and then try to come up with an equation of a line that closely fits these points. And we're going to do all of this with our graphing calculator. So when we are trying to create a scatter plot from a set of data points that we're given, we'll always be given a table of data points, and then we want to tell the calculator how to plot those. We're going to put all of this information under stat. Okay, the stat button is next to the arrows click on stat, and then you want to click on edit the statistics. So stat, and then click on edit, and you'll see these lists. L1, L2, well, my L3 has disappeared, L3, L4, L5. I usually put my X values in L1 and my Y values in L2, okay? I have some information that's already in here. We can get rid of this by just hitting clear or just deleting each of the entries. Do not press delete where it says L1, otherwise it'll delete the name of the column and we don't want to do that. All right. And most of you, if you've never done this before, you probably won't have any information in these parts. All right, so under L1, we're going to put the information that was given to us for the input in the table. That was 0, 2, 4, 6, 8, 10, and 12. Okay. And then under L2, we're going to put all of the outputs that are associated with them. So those are all those decimals. Please make sure that you're taking your time. Make sure that every decimal is exactly written the same way as it's given. We don't even want, what's that? We don't even want one decimal point off. It'll throw off the final answer if it is. Also, make sure that you're pairing things up correctly. So we had 0, 23.76. And then we had 2, 24.78. Next one was 25.93. And then 26.24, 26.93, 27.04, and lastly, 27.93. And you always want to go over your points, double check to make sure that you entered them incorrectly. All right, now we've told the calculator what data we're given. Now we're gonna let the calculator plot the points for us, okay? There's this nice button here that says stat plot. It's above y equals. So basically, usually the calculator graphs the information that's under y equals, but we wanted to graph the information that's under statistics. So we have to tell the calculator that, okay? So we're gonna go to second and then press y equals. That'll open up the stat plots. Some of them may say on or off. We want ours to be on, and we want where it says L1 and L2 here to say L1 and L2. If you have any different list, we have to change that. And basically this is just telling the calculator, hey, I put some statistics in L1 and L2. I want you to plot that. Okay, so our stat plots are turned on. That's good. You can go to each individual one. So plot 1, turn it on or off. We want it on. X list means where are the X values put in. Y list means where the Y values put in. We have those under L1 and L2. If you do need to fix this and type in L1 or L2, L1 can be found above the number 1. So you press second 1, and L2 is under the number 2 or above the number 2. Press second and then 2. All right, so we've told the calculator what our input and outputs are. We've now told the calculator that we want to plot those statistics. The next thing we need to do is go to the graph to see what this looks like. Now, I don't know what my previous window was, but if I just hit graph, it looks like this. So we can see the points there, but it's not an ideal window for the points. If you want the perfect window for your points when you put in your stats information, go to zoom and then go down to number 9. This is what was stated in the book, zoom 9, and that's zoom stat. That will zoom in on the information that you have put under statistics. So zoom 9. Ta-da! This is our scatter plot. So that's our answer for part B. We've graphed or plotted a scatter plot of these points. So once we have this the scatter plot created, the idea is, no, these our points are clearly not in a straight line. However, we can come up with a line that closely fits the points, and it'll be a model or an approximation for the pattern that we see happening with this line. Okay, how do we create our linear regression equation, which is part C? That's what that's asking us. We go back to stat, and then we want to go over to calculate. And you'll see lots of things under calculate, lots of words. We want to go down to number 4, lin reg ax plus b. That stands for linear regression And it tells you that it's going to put the line in the form ax plus b. So click on 4. And then now you have to tell the calculator what statistics you're using for this linear regression. So again, X list should be L1, Y list should be L2. And then that's really all you need. Just hit enter a few times, enter, 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 until you get to calculate. And then it gives you these numbers. This tells you your slope, A is your slope, and then your y-intercept, B is your y-intercept. Now, of course, a couple things. One, this is a very long decimal. Usually we're told to round to either 3 or 4 decimal places for our A and B. And then this just gives us the A and B, but when we write out our answer, we want to write out our answer as a in slope-intercept form. So first, the directions say to round to 3 decimal places. So our equation is going to look like this. Y equals 0.322x plus 24.155. This is the linear equation that most closely fits the points that we have in our scatter plot. Now, before we jump away from our computer, our calculator, I do want to graph this line along with the scatter plot so we can see whether or not it's a good fit. All right, so under y equals, we're going to type in this line. Y equals 0.322x plus 24.155. We're going to graph this, and the scatter plot is still in there, so we'll graph it along with our scatter plot. And let me erase what I have here. Clear. All right. And then ta-da! That is what our graph looks like. So what are we looking for when we look at our graph and our scatter plot together? So when we look at this graph, we're looking for our line to not exactly go through every point, because that would be impossible, because there is no line that goes through all of those points. But the line should be very close to all of the points. So as we can see, like this point is the line goes through it. The rest of them are really close. This one's super close, that one's super close, that one's really close. These ones are a little bit farther away, but still relatively close to the line. So we have a good fit if our the points in our scatter plot are close to the line that we graphed, okay? So we're gonna jump back into our book and talk about how we use our linear regression equation to answer other questions. We did part A. Part B was just creating a scatter plot. We did it on our calculators. Part C was coming up with our regression equation. Also, I use Y and X, but we should use the variables that are given to us in the table. So I should use N for my input. So we'll have f of n is equal to, what was it, 0.322n plus 24.155. And again, I switched from x's and y's to n and f of n because I want to use the variables that are given to us in the problem. Now for part C, once we have this equation, we can use it. It says, use your regression equation to determine f of 6. Write the specific ordered pair associated with this result. So notice, we have f of 6 from the table above. F of 6 that we get from the regression equation is probably going to be different because remember, the regression equation is going to be an approximation. But let's see. So f of 6 using the equation is 0.322 times 6 plus 24.155. And then let's type this into our calculators. 0.322 times 6 plus 24.155. This gives me 26.087. So the ordered pair would be 6, 26.087. Now, let's compare this with what we got in the table. In the table, we had 26.24 for the output. From the regression equation, we get 26.087. Are they exactly the same? No, but they are pretty close. Because remember, our regression equation gives us an approximation for what's happening with the table. All right, and then someone might be wondering, well, if we already know what f of 6 is, why would we use the regression equation to try to figure it out? Good question. We usually don't really use the regression equation for the points that are given to us because we know the exact values, but more so, we want to use the regression equation to figure out what's happening for n values that are not given to us. So for 1, 3, 5, 7, 9, anything above 12, what would the outputs be? For that, we can approximate it using the equation. All right, so your answers to A and Z should be different. Why is this the case? It's because the equation gives an approximation of the data. So again, the equation is a model, it's an approximation, it's going to be close to the information that's in the table, but it's not always going to be exactly the same. Let's see, I think we might have a little bit more. Is there more? There's more. Oh, we already did that part. Part F says use your graphing calculator to graph the scatter plot and the regression equation on the same screen. We did that on our graphing calculator already. Okay, so before I move on, are there any questions about problem 1? Putting in the points for under L1 and L2, creating a scatter plot, coming up with a regression equation, or graphing them together. Any questions at all? All right, team, look at us go. Yay, we did one of our first regression problems. So two very important terms that we need to know when we're dealing with regression problems. So like what we just did a second ago, where we evaluated the regression equation at 6, that is an example of something called interpolation. There are 2 different types of estimates that we get, interpolation and extrapolation. It's basically, it depends on what value you're plugging in. If you're plugging in an input that's within the range, well, I shouldn't say, within the interval of inputs that you're given, then it's called interpolation. What I mean by that, for interpolation, in our last table, we were originally given the points 0 to 12. If we plug in any number between 0 and 12, that would be an example of interpolation. It's inside the interval of n values that we're given. 0 to 12. So n of 6, interpolation. N of 3, interpolation. N of 11, that's interpolation. It's within the input values that we're given. Okay. The other option would be extrapolation. That's if we're finding an output based on an input value that's located outside of the raw data. That means if we pick something less than 0 or bigger than 12 to plug in. Okay, that would be an example of extrapolation. Okay, when we are getting these or doing these approximations, interpolation would give us a better estimate than extrapolation. The idea is if you're using using n values that are close to the data set, then you have a better estimation than if you use raw information that's outside of your raw data. Ugh, I can't talk words today. If you use values that are outside of the raw data set, then you get a worse approximation. So interpolation gives you a better approximation than extrapolation. Problem number 2 has a little picture. It says Niagara Falls is the 2nd largest waterfall in the world and has been eroding naturally for centuries. The following table gives the approximate erosion amount for the Horseshoe Falls on the Canadian side in feet from 1678, when the first measurements were recorded, to 2011. It is worth noting that the measures to reduce the amount of erosion were put into place in 1942. So it was eroding naturally until 1942, and in 1942, they tried to slow it down. So at some point, the data should change a little bit. All right. So the data for this situation is given to us here in our table. We start at the year 1678 and then go all the way up to 2011. Notice we only have a select few years here. In 1678, that's when we were starting. There was no erosion. That was our starting point. By 1819, there was 423 feet of erosion. By 2011, there was 1,107 feet of erosion. Okay. So based on this information, we're asked to determine the regression line. In order to do this, usually when we're giving years as our input, we don't want to have these huge numbers for our input. So we use the starting year as our 0. And we make our inputs the number of years since that starting year. So for example, if we're starting in 1678, the year 1678 corresponds to 0. And then the year 1819, that's 141 years after 1678. So that will correspond to 141. And then we subtract to figure out the difference between the years to find the input values for T. So for 1842, we do 1842 minus 1678. That gives us 164. And then we have 1886 minus 1678, which would be 208. And then we have 1942 minus 1678, 264. And last one, where am I? Oh, 2011. 2011 minus 1678, 333. All right, so these are the values we're gonna use as our input and put into L1. And then for the outputs, we're gonna use the erosion amount in feet. We have to put this into our calculator and then find the regression model. And we can do the scatter plot too, even though we aren't asked. And then notice we're also asked here to use the regression model to figure out the outputs for all of these different inputs that we're given. So to fill in, to use a model to estimate what the erosion amount would be. All right, so we have a little bit of work to do. Let's jump to our graphing calculators and get this done. And then I'm gonna go to stat. Do not, when you go to stat and edit, do not hit delete for L1. So don't go up to L1 and hit delete. Do not hit delete, do not hit delete, do not hit delete. It'll delete the L1 itself. It won't say L1 anymore. So don't hit delete. You can hit clear and then enter. And it'll clear out everything. Or you can go to each individual entry and delete it, but don't delete the actual L1. Clear and then enter. If you do delete it, you can put it back, but try not to delete it. All right, so now for our L1s, we had, let me go back to the book. 0, that's not a 0. 0, 141, 164, 208, 264, and 333. And then for our outputs, we had 0, 423, 538, 758, 1,038, and 1,107. Always double check your numbers. Like me, I always make typos, so I'll always go back and double check, make sure I made no typos. Look, I think I made no typos this time. Go me. All right, and then make sure that each input has a corresponding output. If you want to look at the scatter plot, we can look at the scatter plot, but we're not asked to, but let's just do it. We can go zoom, stat, and we should see the scatter plot. It looks like this. And then to find the regression equation, press stat again. And then remember, we go over to calculate, use the arrow. And then once under calculate, go down to 4. Lin regression. And hold on, I need to see how many decimal places we're asked to round for this problem. Oh, I've gone too far, bear with me. All right, so for problem 2, we're asked to write the regression equation, round it to 2 decimal places. Okay, so hit enter on 4, and then hit enter all the way until you get down to calculate, and boom, this gives us our linear regression equation. So for part A, the answer is going to be, remember, when you write out your equation, I don't want you to write A equals this, B equals this. I want you to write it in slope-intercept form. So let me see what our variables were. We were using T for the input and E of T for the output. So we would have E of T equals (3.58 T plus), or actually it'll be minus because we have a negative there, minus 17.38. This is our regression equation. And then we can graph this along with the scatter plot if we go to y equals and type in this equation. 3.58. We use X for the input all the time, so press that button, X, and then minus 17.38. All right, and then we graph. Your regression equation should always be pretty close to the scatter plot. If you ever get a line that's way off from the scatter plot, that might mean that you typed in something wrong somewhere. Go back and double check. But that's it. So now we have our regression equation, and we have, what do you call it? We have our regression equation, and we have our scatter plot. It looks like a good fit. We can jump back into our workbook. So for our regression equation, and it was E of T equals 3.58 T plus minus 17.38. All right, the next thing we're asked to do is use the regression equation to fill in the bottom of this table. Now we could plug in each value of T by hand and to the equation and use our calculators to help us simplify, or we can make a table of this information to help us do it a little bit quicker. So we're going to use the table on the graphing calculator. I just want to show you a quick way to be able to answer this question. Under y equals, we already have our equation. Now, if we wanted to plug in a bunch of inputs and find the outputs for this equation, we can go to table set. Press second and then window to get to table set. Change your independent variable to ask. That means we're going to plug in the inputs, and then the calculator is going to give us the output. So change it to ask, and then go to table. Right, you see a blank table at this point. This is not the same as where we put in the list L1 and L2. This is where we get the table associated with the equation that we just put in. So under X, now we want to put in the inputs that we had from the previous table. 0, 141. Hold on, let me see what the other ones were. 164, 208, 264, and then 333. All right. So we know the erosion for the certain years that we were given. Using the regression equation, these are the numbers we get for the number of feet of erosion for each of those years that we were given. Notice they are not exactly the same as what we got in the table, but they should be relatively close. All right, so we're going to write this information in the table for part A. Before we jump back into our workbooks, I do want to show you how these numbers correspond to what we saw in the scatter plot and graph? So let's look at the graph. All right, for instance, notice here that for this point, which was at 0, 0, the line is a little bit below 0, 0. So the linear regression equation is going to give us an underestimate. It's going to give us something smaller than what the actual number is. At this point, the line is above, and at this point, the line is above. So for those 2 years, the line or the linear regression equation is going to give us an overestimate, something a little bit bigger than what the original table gave us. This one's an underestimate, that one's an underestimate, I'm sorry, this one's an overestimate. So you can tell based on whether or not the point is above or below the X or the line, whether or not the regression equation is going to give us an overestimate, an underestimate, or the exact number. None of these are exact. All right, so I filled in the information that we got from the table. We found the regression equation. Part B says use the regression equation to complete the table. We did that. Part C says use the regression equation to estimate the amount of erosion in the year 1878. So remember, our input is going to be the number of years since 1678. So in 1878, T is going to be equal to 200, because that's 200 years after 1678, which is where we started. Then from here, we're going to plug in 200 into our regression equation. So E of 200 would be, forgot what the equation is. Let me scroll up. 3.58 times 200 minus 17.38. Then we just simplify this with our graphing calculators. That gives us 698.62 feet of erosion. We always want to explain what our numbers mean and also use units where we can. Okay, part 2 asks us to use the table feature of our calculator to answer this. To use the table feature, we're going to the table, make sure that our inputs are on automatic, and we'll look at 3 rows of the table. One for the input of 199, then the input of 200, then the input of 201. Usually when we ask for answers with tables, we want to put 3 rows. The row with our answer, one above it, and one below it. Our graphing calculators, again, we still have our equation under y equals. I'm going to go in and put our table set on, well, you can have it on auto or ask, it doesn't really matter. Auto will automatically pick the inputs for you. Ask, you have to type in your inputs. So if I go back to the table while it's on ask, I can just look at or type in, I can clear this out if I want, delete, 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 delete. And then we can look at 199, 200, and 201. Okay. We get the same answer for 200 that we got when we calculated it by hand. You should see the same exact answer in the table. For the rest of these, you'll fill in the other parts of your table for part C, or problem C, part 2. So after 199 years, we have 165.4 feet of erosion. After 200 years, 600 and, I said 100, no, I think I said the wrong number, but 698.62 feet of erosion. And after 201 years, we have 702.2 feet of erosion. So once you find your regression equation, the rest of the problems are just using the equation to estimate what's happening for different years. Right, and to just kind of find a good stopping point for this problem, I want to bring this back around to our idea of interpolation versus extrapolation, because we went over those definitions, but we didn't really get to see an example of it. So part D asks us, is the amount of erosion in part C an example of interpolation or extrapolation? Why? So we had T equal to 200 for part C. If we go back, or we were looking at the year 1878. If we go back to our original tables, the years that we were given originally were 1678 to 2011. And then the t-values were 0 to 333. So you're going to ask yourself, is the number I'm plugging in that interval of inputs is 1878 between 1678 and 2011? Yeah, it is between there. So if it's in between there, that's interpolation. If it's outside of these numbers, either less than 1678 or bigger than 2011, then that's extrapolation. But it's within those 2 years or between those 2 years. So this is interpolation. So this would be interpolation. Because it's between the given years. Okay, we won't do these until next class, but notice the next problem asks for the years 2015 and 2030. Those would be examples of extrapolation because they're outside of the given data set.